Welcome to this GERAD webinar. Today we have the pleasure to welcome Professor Antoine Legrain from Polytechnique Montréal for a presentation entitled Nurse Scheduling Problem with Soft Constraints. I'm not going to read the subtitle, I'll let you explain that. But before this presentation, I will let Antoine introduce himself and present as well his research interest. So Antoine, you have the floor.
Okay, thank you very much, Olivier. Hi, everyone. So the subtitle, it was just a teaser to tell you that I was really happy with the results because we were able to solve optimally a 4-week schedule for 121 nurses in 12 seconds. As you will be, we would see it's because the gaps are very small, but we were still impressed by the results. So it's a joint work with several people that I started 6 years ago now. And I will talk a little more about that. And so this is the name of all the person that has participated to this work. They were a member of GERAD. Now Jérémy Omer is a professor in Sarenne, and I'm a professor at Polytechnique Montréal. So a quick presentation of my research interest. So most of my work is on online stochastic optimization. So how to solve dynamic problem with some stochastic information about the future and trying to do that in a very, I would say, managed computing time. And I try to apply that mainly to real-time operation management that are most of the time either in healthcare, for example, appointment booking or inventory management in healthcare, or scheduling too, for example, or transportation, and especially on-demand transportation. So I have several affiliations. So I'm a IVADO professor at Polytechnique Montréal, and so member of IVADO, member of the GERAD. I'm also a member of the chair of Andrea Lodi, and an associate member of the CHUM, or CR-CHUM, the research center of the CHUM, where I conduct a few, I would say, research projects in healthcare. And also, I know many people at the GERAD as I done my master there, and I have some already ongoing collaboration with several members, or perhaps future member, I don't know, for Antoine Legrain, but of the GERAD. So the presentation of today will be, we'll have the following agenda. We will first introduce the problem and also why we solve this problem and why we tackle this problem at the beginning. The different methodology that has been developed through the years, some experiments on the latest results, and some idea about future development and works on this software. So first, the reason why we work on this problem is there were a competition which were called the International Nurse Rostering Competition 2 that were launched in October 2014, and we participate to this competition with Jérémy Omer and Samuel Rosa. And so we had some really good results and worked intensely on this solver for 6 months. And the competition was really on the dynamic aspect of the scheduling. So for example, you have an horizon of 4 or 8 weeks, and the demand for every week was just revealed week by week. And so you have to build the schedule for 1 week, then the scheduling fixed, and you move to the second week when the demand is revealed, and so on. So the competition was really on this dynamic aspect. And one main component of this competition was that we have to use free software for the competition. So that's why we built the branch and prior algorithm based on the project of CoinOR that is called BCP for branch cut and price, and also the Boost library for the managing the resource constraint shortest path. So we release our code and we're still developing it on GitHub, so anyone can access it. And I think it's under an MIT license, so you can do whatever you want with it. And then we tried also to solve the static version of the problem. So instead of solving the schedule dynamically week by week, we were solving at once, for example, the 4 weeks horizon or the 8 weeks horizon. So these two approach leads to 2 papers, one in Azure and one in MPC. So the one in Azure is for the dynamic aspect, is really the work that we have presented and done for the competition. And the second one is more about the static aspect and how we were trying to solve these instances, and especially using an adaptive large neighbor search for it. So let's talk a little more about the problem. So it's a very specific problem, as we will see later on, because most of the constraints are soft and not hard. So we pay a penalty if we do not respect these constraints. So we have a set of nurses. So the instances were from 30 nurses to 120 nurses, and it's individualized nurses. So it means that we have to build a schedule for each one of them. We cannot build generic schedule and then assign them to nurses. We really have to build each schedule for one specific nurse. The reason is that they all have different constraints, or perhaps if you have preferences, they won't be at the same place. And there are some other constraints that makes each schedule needs to be specific to a nurse. So that really increased the difficulty of these problems. The planning horizon was 4 or 8 weeks. We also have some skills. So each nurse is a certain number of skills. So for example, a head nurse can be a head nurse, but can also practice as a nurse and so on. And they can use only one skill at a time when you schedule them. And then you have some contracts. So it's either full-time, part-time, half-time. So it did take the number of working shifts that you can do and some other things. Then you have the work shifts. So in the competition, depending on the instance, you can have up to 4 different shifts, early, day, late, and night. You also have the history. So it means that you need to take into account what the nurse was doing just before the beginning of the schedule. So for example, on the Saturday, just before the beginning of the schedule, the nurse was working perhaps on a night shift, how many shifts she have done consequently, and so on, to be able to compute correctly the constraints that we will see on the 2 next slides. You have also preferences. So do you want to have a day off, or do you don't want to work a certain shift, and so on. And finally, you have a demand. So you have to ensure that you have a certain number of nurses on each shift for each type of skill. And you have 2 demands, one which is minimal and the other optimal. So the minimal is the hard one and the optimal is a soft constraint. So if we look at the constraints, you have 4 hard constraints. The first one is that is a classic one, is the nurse cannot work more than 1 shift per day. So I think any scheduling that you do, workforce scheduling, where you have shift, you don't want to have more than one shift per day most of the time. You have a minimum demand that you must cover. And you have also some sequence of work shifts that are forbidden. So for example, if you have done a night on you have worked on Monday night, you cannot work on on Tuesday morning. But you can do a day on Monday and a day shift on Tuesday. So this one is a little annoying because you have some border effects because of this one. So for example, in the dynamic part, when you were solving the problem week by week, but depending on the scheduling choice that you have made for the Sunday, on the next week, on the Monday, perhaps you don't have so many possibilities because of this legal sequence. So these constraints could lead, for example, to infeasibility for the dynamic part of the scheduling. So this one was tricky to handle. And also a nurse for sure cannot cover the demand for a skill that she does not possess. And so you have many soft constraints. So for the optimal demand, if you do not respect the optimal demand, you pay a penalty for every nurses that are missing. You have also constraints on the consecutive assignment. So for every work period, so for example, if you are working 5 consecutive days, you have a minimum, a lower bound and upper bound on the number of consecutive days that you can work. And you pay a penalty of 30 if you exceed it, or if you are below the lower bound. Same for the not just the workday, but also for the type of shifts that you are doing. So for example, if you are doing a 4-day shift, perhaps you are exceeding the lower bound. For a consecutive day shift, for example, sorry, you're exceeding the upper bound, and so you're going to pay a penalty for it. You have the same idea on the consecutive days off, and then you have also some penalty if you do not respect the preferences. And also you have one about complete weekend. So it means that if you work one day on the you either work both days on the weekend or none of them. If it's not the case, you pay a penalty for it. So I would say that the consecutive assignment here constraints on the assignment and on days off, it's really the main reason why you have to do personalized schedule, because each nurse starts with an history. So it means that she has worked, for example, during 4 days, 2 days on a night shift, or she has been resting for 3 days and so on. And it makes that the pricing of the first shift for each nurse will be different because of that. So depending on the shift you have worked on the Sunday and the day before, on the Monday, you will be priced differently. So you really need to have one, I would say, problem or sub-problem I will see later on for each nurse, especially because of these constraints. And then you have 2 global constraints on the total number of assignments. So if you have a minimum number of assignments and a maximum, and you pay a penalty if you are below the lower bound or above the upper bound. And the same, you have a soft constraint on the total number of working weekends. So the main challenging of this problem is, as I said, it's a personalized schedule. So for example, in a branch and price algorithm, when you have 120 nurses, you have to solve 120 sub-problems. So that's a lot. You have some instances that are for horizon up to 8 weeks. So the sub-problem can have a very long horizon that could be difficult too. And what happened is that the classical resource constraint shortest path that you can use for inside a branch and price algorithm takes time for 2 reasons. So you have the first reason, which is the long horizon, and also because you have many constraints with lower and upper bound, which is really a problem for the classical resource constraint shortest path, as we would see later on. And so we tried in the 2 previous years to develop a specialized algorithm for really tackle this kind of problem with a lot of soft constraints. And we would see that for the competition, we use an approach a little different than the classical approach to try also to tackle this issue with the long horizon and the many soft constraints. So about the state of the art, in fact, there's not so many reference on general soft constraint problems. So you have many references on soft time windows for vehicle routing problems, but they are really different because most of the time in vehicle routing problem, you can wait when you arrive at a certain node. And so the way you handle also this soft time window will be very different than the way you handle time. It's not time window, but the lower bound and upper bound for this soft constraint that we see here. And if we look at that, you have very few. And so our work draws a little inspiration from this reference where they were trying to formalize really soft constraints that you can see in many different problems. So about the methodology, we would start by looking at or remember what is a branch and price algorithm. And then we will look at 2 formulations that we use, what we call a rotation generation subproblem and decomposition, if you want, by roster, which is more the classical decomposition that you can see in when you do column generation. And then we will look at the algorithm we developed for the soft resource constraint shortest path. So first, a branch and price basically is just column generation at every node of the branch and bound tree. And what is column generation is you solve the linear relaxation of a problem where you have just a certain number of columns that represent the different solution that you have. And based on the dual value of this linear relaxation, you would solve some sub-problem. And then this subproblem will give you new columns that you can add to the master problem. And you will only add these columns if they have a reduced cost, which is negative here in the case of a minimization problem. And if you don't find any column with a negative reduced cost, so it's the same that if you don't find any variable with a negative reduced cost when you do the simplex, you just stop and you have the optimal solution for the linear relaxation. So you do this process at every node in the branch and bound tree when you do branch and price. So let's first define what is a rotation. So the name rotation and the ID comes a little from the aircrew scheduling literature, where you have a plane that starts from a hub that will do, for example, several flights at several airports and come back to the hub. So instead of generating the schedule of an employee, for example, for the whole month, you would just try to schedule tiny pieces that correspond to a schedule that starts from a hub and come back to the hub. So here it's a little the same idea. We will just build schedules that are a sequence of work days, but we do not take into account the rest days when we do this generation. We just want a sequence of work days. And it's what we call rotation. So for example, in this schedule or roster, you have 2 rotation and the rest are rest days. So we will generate only this rotation in the first approach. The main advantage to do that is you generate paths that are much smaller in the subproblem, so it's easier and takes less time to generate them. So if we look at the decomposition of the constraints that we do, you have in the subproblem, you're taking into account the hard constraint 1 and 3, so which is you want just 1 shift per day, and you take into account the legal transition between shifts. And you take also into account everything that is related to work and consecutive work. So consecutive assignment, preference, and complete weekend. Then in the master, you take into account the demand, you take into account also the skills, and you take into account everything that is related to days off and the global constraints on the total number of assignments and weekends. So the way you manage skills is you look at the nurse could be gathered by position. So it means that all the nurses that, for example, have the skill head nurse and nurse will be gathered together, and you will count on every day and every shift the number of this type of nurse that are working. You do that for every different type of shift of nurses that you have. And then you just have an allocation problem where you allocate these nurses to the skills. So the allocation of the skill is just a network flow problem that you add in the master problem, and you can see if you meet or not the demand, and also if you cover or not the optimal demand. Then it's a little more complex for the rotation, because now you cannot just select 1 rotation per nurse. You have also to build the sequence of rotation and days off. So you also have a graph for that, and it's also a flow. So, for example, here on 1 week, you start from the sink here, which is the day 0, and then you would just either have some days off, then a rotation, which is here a sequence of 2 days work days, then 2 days off, then another 2 days work, and what will happen is we will just enumerate all the possible sequence of days off and price them correctly. And then the rotation are the part that is generated dynamically by the column generation. So in fact, what we do here, we are dynamically generating the arc corresponding to the rotation in those graphs for every nurse. So you have 1 graph like that for each nurse. And then the main issue, so the main advantage of this representation is that you shorten a lot 2 things that we will see. The resolution of the subproblem is way faster because you just generate very small path. And the second thing is also you have to generate way less column, because you can reuse some of the rotation in different combination of schedules. And the master problem is doing these combinations of days off and rotations. But there is one main drawbacks with that, is that the constraints on the total number of assignment and work weekend is now in the master. And so you will have an important integrality gap because of these constraints. So that's really the main drawback. So you gain in terms of speed, resolution speed, but you lose a lot in terms of quality of the linear relaxation. So if we look at the subproblem that we use for the generation of the rotation, you have this kind of graphs where you have every day the different shifts that are representative. And so here, for example, for early, you can go in early, late, or night, but night you can only go to night. So all the legal transition between shifts are represented here in the graph. And then you have one source and one sink. And from one source, you can go to any of the nodes. So you can start on any day, and you can stop on any day also and go to the source. So you're only working here, you cannot rest. So now let's look at what we will do if we want to do a roster generation instead of a rotation generation. So a roster is the sequence of days off and rotation that we see. So here you will get a full roster here with the 2 rotation and the sequence of days off. So now we will be generating these rosters instead of generating the rotations. The main advantage of doing that is you are putting way more constraint in the subproblem, and so you have a linear relaxation that is stronger. So as we can see, here on the right, you have how the constraints were split between the subproblem and the master problem. And we can see that now we are moving the constraint on the consecutive days off and the total number of assignments and weekends inside the master problem, inside the subproblem. It means that you cannot cheat anymore, especially on these 2 constraints. So you have to pay the real price according to this constraint. And that's why the linear relaxation will be much stronger for this problem. And if you look at the roster generation, so we are taking back exactly the same graph, but we are adding now the rest nodes, and we are also adding arcs from rest to any shift and from any shift to rest. So now you can really have a full roster that is generated by this graph. The main difference here is that the source is only connected to the to the nodes that are on day 1, and the sink is only connected to the last day. So it means that you really have to have a path that starts at the beginning on the first day and go until the last day. So the length of your paths are much longer than in the previous graph. That's why it takes much more time to solve it. So to overcome this challenge, we develop a new domination rules to really be able to speed up this resolution problem and take advantage of the soft constraints that we have. So let's take a simple example where you have only one resource, one label, which is the consecutive work days with a lower bound of 2 and upper bound of 5 and a penalty of 30. Let's take this green node here, and let's suppose that we only have 2 labels that arrived at this node. So the first one has a cost of -100 and for the resource a value of 2. And the second label has a cost of -200 and a label value of 1. What will happen with the classical domination is nothing can be said, and label 1 cannot dominate label 2, and label 2 cannot dominate label 1. The reason is that label 2 has a greater cost, has a better cost than label 1. So, and this resource is also smaller. So you may want to try to dominate this label. You may want to say that label 2 dominates label 1. But the issue here is that you also have a lower bound. And so imagine that you just stop work now, or you go to a rest. you will pay a penalty for the second one. And if you were using hard constraints, the second label will be infeasible. And so classical domination has been more built for hard constraints. So in this case, if we were looking at hard constraint, label 2 doesn't dominate label 1, because if we stop here, label 2 is infeasible, and so you cannot use it. That's why you cannot say anything in this case. But our case is different. We have soft constraints, and so you can violate lower bound and upper bound, but at a penalty cost. So let's do some worst case analysis here. If you stop to work immediately and you go to the rest node here, you can compute the costs related to that. So the first cost will remain minus 100, because here you are just at the lower bound, so you don't pay any penalty for the resource. And here, because you are just below the lower bound, you pay only 1 penalty. And you can see that the second level still remain better than the first one. And the second worst case is that you work 4 days until the label 1 exceed the upper bound. So what happened is you will just exceed of 1 penalty. So you have paid 1 penalty minus 70 for the cost. And here you are just at the upper bound with a resource that has a value of 5, so you don't pay anything. And you can see that in the both extreme worst case, label 2 is always better than label 1. So we will use that to do a better domination in the graphs. So if we formalize a little that, what we say is that for every resource that we have, every soft resource, we compute the worst case. So the worst case, in fact, is just the difference between the value for the label 1 of this resource and the value of this resource for label 2. And so we just take the absolute value of this difference and we multiply that by the penalty. And so that really gave us the worst penalty that you can get for this resource and between these two labels. And then when we want to compare label 1 and label 2, you take the cost of label 1 and you add the worst case penalty that you can get for all the resources. And if you are still below the cost of label 2, it means that label 1 effectively dominates label 2. And you can do the same in the other way. If you have the cost of label 2 plus the worst case possibility for all the resources, and even in this case, you are still lower than the cost of label 1, label 2 dominates label 1. And if you are in the middle of both, nothing can be said, and you will keep both labels at the node. And so the reason why it's way better to do that is you can dominate way more the graph. And so you have way more label at each node. And so the resolution, as we will see, will be way faster thanks to these domination rules. So let's look at some experiments. So first we look at on some instances, small instances, we look at the different approaches and try to see how you can gain. And all the results that will be presented for this analysis is always an average over 30 runs. And then we use the full benchmark that we have with NRC2 instances, and we look at what we'll get with the Worcester approach with soft domination. So I didn't have time, I think, to compute the biggest instances, but you will have results for most of them. So let's look at the speed up that you get by doing soft domination compared to classical one. So here it's for the roster approach. So we have used the 3 small instances, one with only 5 nurses over 4 weeks, here 30 nurses over 4 weeks, and here 12 nurses over 8 weeks. So each point here corresponds to the average speed up that you get when you compare the soft domination to the classical domination. And each point corresponds to exactly 1 nurse. So here you have 5 points for 5 nurses, 30 points, and here 12 points. The color that you have here correspond to the contract of the nurse. So here you have a 3 full-time nurse and 2 part-time. here full-time, part-time, and half-time, and here full-time and part-time. So what you can see is your very good speed up for most of the cases. So I think here you have a speed up around 10, and here it's a bit around 40. And you can see that over the 8 weeks, you can reach some speed up over 200. So it means that you are able to solve the same problem, the roster problem, 200 times faster with the soft domination compared to the classical domination. So it changed everything for the branch and price approach. The other thing that is interesting here is to compare the color code. Is in fact the half-time nurses have bounds that are much smaller on the total number of assignments that, for example, the full-time. And so when you compute the roster, you have a lot less work shift inside the roster. And so that's why the classical approach is able to have better results for that. And also it means that the resources are taking less different values, that also you have less labels. And so you can see when the total number of assignments or the bounds for the total number of assignments increase, the solving time increases as crazy, especially here you can see the difference. And what is interesting that you don't see in this figure, but when you are doing soft domination, in fact, the algorithm doesn't care about the total number of assignments because they are able to, in any case, to dominate efficiently. So the solving time remain in average the same for all these nurses. So it's really the classical approach that makes a huge difference between the full-time here, for example, and the part-time, especially on 8 weeks. So then we compare still between the classical domination and the soft domination, but also for the rotation and the roster approach. So we solve the linear relaxation for just a very small instance of 5 weeks of 5 nurses over 4 weeks. And we look at the difference in terms of number of columns that's been generating, number of iteration, the time needed, and the objective value. So the first thing that we can see is that for sure here the roster is a little better than the rotation in terms of linear relaxation, and on bigger instances, it's the difference is way bigger than that. And you can see here that with the classical domination, the roster approach takes a lot of time. So we are on a very small instances with only 5 nurses over 4 weeks. And already here, you need nearly 30 seconds just to solve the linear relaxation when you do the roster approach. And you have more iteration and more columns for the rosters. But when you do soft domination, you still have more iteration for the roster and more columns. But as you can see, the computational times are very similar. And here you have a speed up of a factor of 30 here, just by doing soft domination on these very small instances. So what it means is that now we are able to really use in a branch and price algorithm the roster approach with these times, computational time. But here we were not, because on bigger instances, it was really taking way too much time to solve the roster approach. So we also try to develop a different strategy to speed up the resolution of the shortest path and with soft domination. So the first idea was to remove some resources. Is something that we classically do when we are solving this type of problem, and we are just creating more arcs to enumerate the value of these resources instead of having keeping the resource inside the labels. And so when we do that, we can see that in fact we have a speed up that is less than 1. And you can see here it can be really bad. It means that we are taking here, this approach is taking more than 2 times the time where we are not using it. So it doesn't really work with soft domination, the idea of enumerating the resource and removing it. I think it's because the domination is really working well. And so even if you have you are just in the middle of the consumption of this resource, you are still able to do a good domination. So the subpass is just taking time because you're creating more arcs, you need to enumerate all these arcs and so on. So it increases the resolution time of the subproblem. So here, the idea was to evaluate for every node what was the shortest path just in terms of cost to go to the sink. And the idea is when you are at a given node, you look at the cost and you look at the minimum cost that you can get to reach the sink. And if this cost with the cost to go to the sink is positive, it means that you won't be able to generate a column or here a roster with a negative reduced cost. So you can just not dominate, but prune, remove the label. This one didn't really work also. I think the small decrease that you can see here is just due to the fact that you have to compute all these shortest paths, so it takes a little time. And I'm pretty sure that once computed, it doesn't really help the algorithm. And you have also to do some operation to add that every time. So in fact, you are decreasing also the computational time or the resolution time for this problem. And then we try to combine both to see, oh, okay, so this one is not working because you have too many arcs and the domination is already doing a good job, so no need. Oh, this one is not working because here we are only taking into account the dual value and the cost of the arc. We are not taking into account the cost of the resources. So let's try to do the enumeration of the resources and then compute the shortest path in this graph. So like that, we also take into account the cost associated to the resources. But we're still resolving the same graph where we don't have the enumeration of the resources. We just do that to compute the shortest path. And it's the same. We can see you lose time by doing so. And I think the reason is always the same, is that the soft domination, in fact, compute a kind of approximation of the cost that you will get. And so you are not able to do better by computing this cost because you're already kind of computing them when you are doing the soft domination. And also, I think the other reason is you are always, most of the time, able to find paths where you are not consuming you are not paying any penalty for these resources. So you are not adding anything. So as a conclusion for this part, we just use the base version without any of this feature when we were resolving the branch chain price after that. So we use the benchmark where we it's not 35, sorry, here it's 30. So we have from 30 nurses to 120 nurses. The horizon is for 8 weeks, and there are several scenarios of demands for for each instance. We use the 4 CPU and we run the test on a machine that has 6 CPU. And we use also BCP and CLP, which is the linear programming solver of CoinOR. So I'm pretty sure that this result could also be improved if we were using Cplex or Gurobi instead of CLP. So the first one results that you can see here is for the 4 weeks horizon. So here, the first columns that you have are the results that we published in the MPC journal. It was related to the static version of the problem, and it's the result we got with the ILNS version of the problem. So we're implementing a large neighbor search over the branch and price where we were using the rotation decomposition for it. And so what you could see here is that the rostering approach with the soft domination is really beating everything. So all the columns where we are in bold means that we have better results than the previous results. And all the ones that are in italic also means that it's an optimal solution. So the lower bound is equal to the lower bound, the upper bound. So you can see here that most of the instances are closed, in fact. So the only one that remain not closed are this one this one and this one. So you have 4 instances that are not closed, and you can see that the gaps are really, really close. We are just missing 5 every time. And so 5 correspond to the minimum penalty because all the weight that we have in the problem are multiple of 5. So it means that either we could increase the lower bound, or either we could only gain 1 unit for a certain resource at a certain place. So it's just over 1 penalties that we could gain here to be able to reach the optimality. So we are really, really close to the optimality in all the solutions where we have not proven the optimality. And you can see that most of them are solved in a very, very short computing time. So as I said, the biggest one here, so 4 weeks and 120 nurses is just solved in 12 seconds. And we can see that with the previous version and the rotation, we were really far from the optimal, either for the lower bound or for the upper bound. And so we can also see here that the linear relaxation of the raster approach is much stronger than the one we use with the rotation, because you have a huge difference here between the 2 lower bounds. And the reason why we're able to do this very short time is, in fact, the linear relaxation is already the lower bound of the solution. You can see here we just a little over 45, so we can round up that to 2050, which is the lower bound, and the upper bound, so the optimal solution. It means also that we have been able to find this solution really quickly also. So perhaps at the root node or just after very few iterations. And so we are able to solve most of the instances in a very small computing time. You can see that some of them we are not able, we still need time. So this one is interesting. We can see that here we are missing, so this one, if we round this lower bound, we have 2015. So we are missing 5 units to be able to reach the lower bound. So you can see that the algorithm needed half an hour to be able just to increase a little the lower bound to this level. So it means here that perhaps we have the optimal value, but in 1 hour, we haven't been able to increase sufficiently the lower bound. So here, for example, we can see that we started at 35 and would be able to increase the lower bound to 35, but we are still missing 5 to close the instance. So if we look now at the results on 8 weeks, they are much different. So we are still able to get way better, not way, I would say better results for the roster approach. So the lower bound is still way better than the one we had previously. It's just because the linear relaxation is really stronger for the roster approach. But if you look at the upper bound, we have most of the time the best upper bound here, but they are much closer. So here, if you look this one and this one, you only have 30 of difference. And you have some other where you have only, I think, 5 of different, 10, for example. So this one, you only have 10 of difference. And even in this case, the ILNS was able to find a better solution than the new approach with the roster. So we can see that when the number of weights increase, it still remain really difficult. And solving the 8 weeks and just the linear relaxation for the big instances still take time. So we're talking several minutes just for the root node for the biggest instances. So the take-home message that I hope you will remember from this talk is that really the soft domination has sped up the resolution time by 250 if we compare for the roster approach. So it's really what makes the difference and enable us to solve to optimality most of the 4 weeks instances. And thanks to this domination, the roster approach is now computationally manageable, which was not the case before. And we have a very, very tight lower bound. That's why we're able to solve to optimality most of the instances. And as we can see in the 4 weeks, for the 4 weeks instances, they were mainly most solved to optimality except I think 4. But it means also that the rotation approach and the ILNS approach remain still a very good option for big instances, and especially instances where you have more than 8 weeks. So let's think if you have 12 or 16 weeks, you can still manage them with this approach in the rotation approach, but I'm pretty sure they won't be manageable with the roster approach, because even with soft domination, computing a roster over 16 weeks is really difficult. So the future development on which we hope to work is to implement strong branching as in the current strategy, because the current one is not really stable. So for example, there is some random aspect in the selection of the variable on which we are branching. And if you change a little this random aspect, some of the 4-week instances, for example, cannot be solved optimally, and some could be. So for example, to be fair, I didn't present that here, but one of the 60 nurses instances where we're not able to solve optimally here. In some other tests where we had another seed, we're able to solve them optimally in less than 2 minutes. So there is a lot of instability because of that, and I hope that strong branching will help to resolve perhaps part of this instability, and perhaps be able to close all the instances that we were not able to close in the for the 4 weeks. We are also trying, so as you see, I'm talking about the ENRC2, so it means that there were an ENRC1 also. So we want to try to be able to tackle also these instances. And also I'm doing some advertisement. I'm looking for a PhD to work on stochastic integer optimization for this problem, to handle the uncertainty that we can have on the demand, and especially there is a part I'm trying to work in collaboration with the SHUM, is when you have patients that remain a certain time in your ward in an hospital, you want, if possible, to minimize the number of nurses that see this patient. So you can minimize the number, the risk associated, and also it's nicer for the patient because he can see from one day to the next the same nurses. So it's especially true, for example, for intensive care units where the patients are in very critical condition. And if you can minimize the number of nurses that take care of this patient, it can really lower the risk and improve the care that you offer to these patients. So the idea would be to take into account the patient that comes inside the ward and the time they stay inside the ward, to optimize the rotation of the nurses. So when the nurses start a rotation and end a rotation, to be sure, for example, that not all the nurses stop their rotation at the same time, and so you have a totally the number of different nurses that start on the day after, and so you will be sure like that the patient will have different nurses. So try to have a good alternance between this beginning and end of rotation, so we can perhaps increase or decrease the number of nurses that are being seen by the same patient. And also, ideally, I'm trying to find some student to develop a web interface so we can plug the solver directly in the web interface, and perhaps some hospital or some clinics can try to use them to build their schedule if the constraints they have are implemented inside the solver. Thank you very much for your time, and I will answer happily to any question. Thank you.
Thank you very much, Antoine. Very interesting presentation.